In this video, we're going to take a look at comparison tests for determining convergence or divergence of infinite series. And for this particular lesson, there's a few series that you need to be familiar with. The first is the infinite series 1 over n, which is the divergent harmonic series. The second series you need to know will be the sum of the terms from 1 to infinity for the geometric series, a times a common ratio to the n minus 1, which converges when the absolute value of the common ratio is less than 1. And finally, we need to be familiar with the p-series. Anything expressed 1 over n to the p, where p is some constant power. We need to know that the p-series converges for all values of p that are strictly greater than 1, and diverges for any values of p less than or equal to 1. And the case where p equals 1 is the divergent harmonic series we mentioned above. And the idea for this lesson is that convergence and divergence for many types of series that we look at can be accomplished by comparing those series to these base cases. These are easy series to work with, and we can use that to make tough problems a little bit more simple. So the first comparison test is what's known as the direct comparison test, which states that given two sequences, a sub n and b sub n, such that a sub n is between 0 and b sub n, so all terms for a sub n are positive and smaller than all terms for b sub n, for all n greater than what we're going to call capital N, which is just some large cutoff number where for everything beyond this value, b sub n is larger than a sub n. So b sub n doesn't always have to be larger, it just has to eventually be larger. And how the test works, it states that if the infinite series for b sub n converges, then the infinite series for a sub n must also converge. And put more simply, if the larger series converges, the smaller series must converge. If the larger series has a sum that's a finite value, anything smaller must also have a sum that's a finite value. And the other side of the direct comparison test states that if a sub n diverges, then the series for b sub n also diverges. And again, to put this in simple terms, if the smaller of the two series diverges, the larger series must diverge. If a smaller sum is infinitely large, then the larger sum must also be infinitely large. And we'll start with the following example. And for this example, we're trying to answer the question, does the infinite series 1 over n squared plus 2 converge or diverge? Well, this series resembles the infinite series 1 over n squared, which is a convergent p-series because p is greater than 1. And we can note that every term for 1 over n squared plus 2 is less than every term for 1 over n squared for any value of n greater than or equal to 1. And we know this because In the new series, we're adding 2 to the denominator, but we're keeping the numerator the same. A bigger denominator is going to mean a smaller number overall. So we will conclude by the direct comparison test that the series 1 over n squared plus 2 also converges. All values in the series are less than a larger convergent series, so this new series must also converge. Let's do one more example with the direct comparison test. And in this example, we're going to ask, does the series starting from n equals 3 to infinity for 1 over n minus 2 converge or diverge? And notice we have to start this at n equals 3 for the index because this series is undefined at n equals 2. And so right now this series resembles the harmonic series 1 over n, a series which we know is divergent. All the terms for 1 over n minus 2 are greater than the terms for 1 over n, because we are dealing with a smaller denominator than that series 1 over n. And this is true as long as n is greater than or equal to 3. Again, just working off the index that we started with on the original problem. By the direct comparison test, the infinite series from 3 to infinity for 1 over n minus 2 also diverges. Since that series is greater than a series that we know to be divergent, that has an infinite sum, this series must also diverge. And we're going to look at one more example to show an issue that develops with the direct comparison test. And so we'll finish this part of the lesson by looking at the series 1 over n plus 4 to see if that converges or diverges. Now, just like example 2, this series resembles the infinite series for 1 over n. Again, looking at that divergent harmonic series. But here's where we run into an issue. 1 over n plus 4 is less than 1 over n for all n greater than or equal to 1. And why this will be an issue is that a series having a value that's less than a divergent series does not guarantee that it is convergent. Just because something's less than an infinite sum, it could still have an infinite sum itself. And so this direct comparison test is severely limited if we can't prove that our series is greater or less than a comparable series to prove our point. But the comparison test has a better version that we can use. And this other comparison test is known as the limit comparison test, which states that if a sub n is greater than 0 and b sub n is greater than 0, so both those original series that we discussed earlier have terms that are all positive, and the limit as n goes to infinity for a sub n divided by b sub n equals L, where L is positive and finite, then the two associated series for a sub n and b sub n either both converge or they both diverge. And the reasoning behind this and why we can use the limit of this ratio is that this test compares behavior of the terms in both series at large values of n. And if the limit exists and is finite, this means that all terms of one series are essentially a constant multiple of the terms in the other series at very large values of n. And therefore, the sum of the terms will also essentially be a constant multiple of the other series sum. So either a constant multiple of a convergent series or a constant multiple of a divergent series. And that's why the results are going to come in pairs. Both converge or both diverge. So let's revisit example 3 using this new comparison test. Remember that we're trying to look at the infinite series 1 over n plus 4. So just like the direct comparison test, we pick out a series that resembles this one. So we'll focus on the divergent harmonic series 1 over n to make our comparison. And we'll set up for the limit comparison test, taking our original series 1 over n plus 4 and dividing by our comparison series 1 over n, which will be equal to the limit as n approaches infinity for n over n plus 4. And this limit does exist and is equal to 1. So since this limit is positive and finite, and the series 1 over n diverges, then the infinite series 1 over n plus 4 must also diverge. So notice it's a very straightforward test to use if you're comfortable with infinite limits. And just like with the direct comparison test, all it relies upon is your ability to see what a particular series would resemble, that comparison series that we want to use to prove our point. So let's finish with one more example. Does the infinite series 2 times the square root of n all over 5n squared minus 7 converge or diverge? And the reason why I want to bring up this example is this one's a little bit tough to tell what we should use to make the comparison. So one thing that we might need to do in order to figure out that comparison is to consider the limit as n approaches infinity for our original series. But not so much the limit value. The limit value on this would be 0, which would simply allow us to pass the nth term test. What I want to focus on instead is the behavior at infinity. And at infinity, the minus 7 in that denominator isn't going to matter. It's going to be too small to alter the value. So this series will act like the series 2 square root of n over 5n squared for large values of n, which will be equivalent to 2/5 times the limit as n approaches infinity of 1 over n to the 3/2 power. So if this series is eventually going to act like 1 over n to the 3/2 power, that is the series we are going to use to make our comparison. And this comparison will be helpful because this is a convergent p-series. P in this case is greater than 1. So we will evaluate the limit as n approaches infinity for 2 square root of n over 5n squared minus 7 all over 1 over n to the 3/2 power. Flipping the bottom fraction and multiplying will yield 2 square root of n times n to the 3/2 power over 5n squared minus 7, which will become 2n squared over 5n squared minus 7. And the limit of that expression is 2/5. So since the limit is finite and positive, and since that series 1 over n to the 3/2 converges, the series in question, 2 square root of n over 5n squared minus 7, must also converge. And that's it for this lesson on comparison tests. Again, the limit comparison test is probably the more useful one because you can use it in a much wider array of examples. But the direct comparison test is there if it's easy to make that direct comparison of one series being larger or smaller than another. That's all I have for this one. Thank you for watching.